morning, friends. Today we are going to discuss about testing of materials, in particularly tensile testing. The session learning outcomes objectives are the concept of testing of materials, particularly tensile testing. At the end of this session, the student must be in a position to explain the concept of tensile testing and its procedures. Actually, testing considers about two types of testing. One is destructive testing, another one is non-destructive testing. While we having destructive testing, the changes of dimensions or physical or structural integrity of the specimen is being explored. It is essentially destroyed the specimen during the testing. Examples are tensile, compression, shear, and Rockwell harness testing. While non-destructive testing, which does not affect the structural integrity of the sample. For example, a measurement that does not affect the specimen in any way, example, weighing or other measurements, length, breadth, height. So this type of testing will not affect the specimen and its performance. While destructive testing, it destroys the specimen during the testing. Tensile test is a common type of materials test, normally do for metals, wood, plastics, and most of the other materials. Tensile tests are those that tend to pull the specimen apart, putting in a specimen in tension. Can be performed in any of the specimen of known cross-sectional area and known gauge length to which a uniform tensile load can be applied. And tensile tests are used to determine particular mechanical behavior of materials under static, axial tensile or stretch loading. These tests are performed as per the American Society for Testing and Materials standard. For common tensile test may be found in sections E8 for particularly metals and D638 for plastics and D2343 for fibers for composite manufacturing and D897 for adhesives and D987 for paper and D412 for rubbers. So these are all the ASTM specifications for different metallic and non-metallic materials. And mechanical property that can be extracted or identified by using a tensile test are ultimate tensile strength. This is the maximum tensile stress that the material can absorb or capable of developing during the tensile test. And load is the applied force either in pounds or Newton. Stress is the intensity of internally distributed force or component of the force that can resist the change of the dimension of the body. Commonly measured in units dealing with force per unit area such as pounds per square inch, psi, or lb per inch square, or MPa. The three basic types of stresses are tension, compression, and shear. The first two, tension and compression, are called direct stresses, and the another term called elastic limit. The greatest amount of stress the material can develop without taking permanent set is called elastic limit. Percentage elongation, the total percentage of the strain that a specimen developed during the tensile test. And the principal properties that can be determined through tensile testing, which includes yield strength, tensile strength, ductility based on the percentage elongation and percentage reduction in cross-sectional area, and modulus of elasticity and visual characteristics of the fracture. For brittle materials, we do not show the marked yield or ductility. Data is collected for tensile strength and type of condition of the fracture. The tensile testing procedure are tensile tests are usually used to determine the tensile properties of the material, which includes tensile strength, the tensile strength of the material in the maximum stress that can be developed in the material. In order to conduct the tensile test, the proper specimen must be obtained. This specimen should conform to ASTM specification for its standard size and features prior to the test. The cross-sectional area may be calculated and the predetermined gauge length are marked. The specimen is then loaded into the machine set up for a tensile load and placed on the proper grippers. Once it is loaded, the machine can then be used to apply a steady continuous tensile load. Then the data is collected predetermined points of increments during the test. Depending on the material and the specimen being tested, data point may be more or less frequent. Data include the applied load and the change in the gauge length. The gauge load is gradually read from the machine panel in pounds or kilograms. These are all the standard specimens. The first one shows the cylindrical specimen of smooth tensile test, and the second one shows the notch tensile test specimen for cylindrical geometry. While this is the flat geometry, cross section is having rectangular cross section. This is normally conducted for a flat specimen, plate specimens, and this is a notch tensile specimen for this flat specimen. Here the tensile test can be done in two ways. One is called smooth tensile specimen. This is called to identify the various mechanical properties as discussed in the previous case. And the notch tensile specimen are used to determine the notch sensitivity behavior of that particular material, whether to identify this is notch tensile material or notch brittle material. When the notch is provided, how it behaves can be estimated by using this notch tensile specimens. The change in gauge length is determined using an extensometer. An extensometer firmly fixed into the machine or specimen, and related amount of deformation or deflection can be in between the gauge length during the test. While paying the close attention to the readings, data points are collected until the material starts to yield significantly. This can be seen when deformation continues without having no increase in applied load. Once this begins, the extensometer is removed and the load continues until failure. Ultimate tensile strength and rupture strength can be calculated from this lateral loading. Once the data have been collected, the tensile stress developed and resultant strain can be calculated. Stress is calculated based on the applied load and the cross-sectional area, while strain is calculated by using the change in length and to the original length. So expected results from the tensile test are: the results of tensile testing can be used to plot a stress strain curve with the illustrate the tensile properties of the material. Stress normally used to notated in pounds per square inch or Pascal is plotted on the vertical axis, while strain inches per inch, millimeters per millimeter or unitless is plotted along the horizontal. As the load is applied, the curve is proportional, and this period of linearity is termed as elastic region. Once the curve deviates from the straight line and begins to yield, the material has reached the proportional limit. Once the material yielded, it exhibits plastic behavior or plasticity. Brittle materials do not exhibit such a kind of yield and are therefore less curved than ductile materials. So modulus of elasticity, also known as Young's modulus, calculated by finding the slope of the stress strain curve within the elastic limit. And proportional limit is the greatest stress a material can develop without deviating from the linearity between stress and strain. Otherwise stated, the greatest stress developed in a material within its elastic range. Percentage reduction in area, the difference between the original and final cross-sectional area of the tested specimen, expressed in percentage. Yield point, also referred as elastic limit, is the point at which any additional stress will result in permanent deformation. Yield strength is the stress at which the material exhibits a specified limiting permanent set. And engineering stress is called as sigma equal to load by area. P is the load in pound or Newton on the specimen. A naught is the original cross-sectional area near the center of the specimen. On the other hand, the true stress is the load divided by true area, which continues to be smaller by the tensile load. The true stress continues in increase to the point of fracture, while the engineering stress decreases to the point of fracture due to the increase in load and constant cross-sectional area. The engineering strain is eta E equal to L minus L naught divided by L naught, where L is the gauge length given at the load, L naught is the original gauge length with zero load. Modulus of elasticity, the slope of the stress strain curve in the elastic deformation region is the modulus of elasticity, which is known as Young's modulus, E equal to sigma by strain eta. And this is the material fracture background stress strain curve, which is related to same material. This is engineering stress strain curve, this is true stress strain curve. So as we discussed in the previous slide, engineering strain is continuously decreasing while the cross section is continued to be maintained as same, the original cross sectional area. In true stress strain curve, the strain is continuing to increase because here the cross sectional area is continued to decreasing. This is because of necking. In the ductile failure, we have seen this formation of necking. During the necking, the cross sectional area is continued to decrease. This is being considered in true stress strain curve, which is not considered in engineering stress strain curve. Is the reason why after ultimate strength the strain level is decreasing. After the ultimate stress also the strain is getting increased in true stress strain curve. Is the reason the in true stress strain curve, true stress and strain is being considered after the necking with the original cross sectional area, while in engineering stress strain curve the initial cross sectional area is being considered, the load is decreased, area is maintained same. And this is the video graph which shows the experimental procedure of tensile testing.
Conducting tensile test, 500 diameter tensile specimen, stainless steel material. Engage tensile specimen between crossheads. Apply extensometer to determine yield strength of material.
Computer control is now the continuous monitoring of strain is being plotted in this area. You can see strain is started when the system is being started. See here is the curve. Yeah, the yield is started now. So we can remove the extensometer.
After yield strength has been determined, remove extensometer and continue test to failure.
Now you can see the formation of necking in this area. Yeah, necking is formed here, you see. Necking is formed, and now the fracture is going to occur. Excellent. Specimen is removed. Now we can observe the length before and after. Diameter is measured to identify the percentage reduction in cross sectional area. Yeah, you see here, this is the curve which is given from the computer, which is continuously monitoring the stress versus strain relationship. This curve is belong to pure ductile material, and the curve under the curve, area under the curve is to be used to measure the impact toughness of the material. And this point, up to this point, this is called your yield point. Until here the elasticity is there. Once the load is removed, the material regain its original position. After that there is a plastic deformation. This point is called yield point. And here after that there is a increment in the continuous load and the stress level, which is called your ultimate strength, and this point, the stress corresponding to this point is called fracture strength, and this region is elastic region, and this particular region is plastic region. So until now this is temporary deformation, after that this is a permanent deformation, and we can calculate this is your ultimate elongation and this is your yield elongation, the strain level. And this is another important property of the material. This is elastic region, this is yielding, this is strain hardening region, this is necking region. After necking, the load is decreased. So this is engineering stress strain curve. So sigma u is ultimate stress, sigma f is fracture stress at this location, sigma y equal to yield stress, sigma pl is equal to proportionality limit. And these are all the specimen photographs. During the test this material will be like this, during the test it will forming necking. So the necking is clearly photographed in these pictures, which we have seen in the videograph also. So stress strain curve for a different material, one should clearly understand that the stress strain curve will not always be like this in the previous slide. So this is true for a low strength, high ductility, low toughness material, because the area under the curve is your indication of your, this area under the curve is the indication of your impact toughness. So this curve, low strength, high ductility, it offers very high strain. So high ductility, low strength, so low impact toughness. And the second curve belongs to high strength material, which offer high ductility too, and toughness value is again higher. So area under the curve is high, and this is for stress strain curve for a high strength material, and it offers very low ductility and low toughness. So this is belongs to for martensitic stainless steel or martensite steel, when the heat treatment is offered, which can offer very high strength. In that case the ductility will be poor, which we have seen in our other classes of materials also. So this is true for very low strength material, which offers high ductility for in case of pure iron, and this is true for most of the materials, high strength and high ductility and high toughness. Thank you for your patient listening, and keep learning.